Welcome back to Mass Transfer Operations 2 course, and we were discussing on leaching process, that is solid liquid extraction. Now, we will be discussing on the last topic, that is supercritical fluid extraction and equipment for leaching. So, first of all we need to understand the meaning of supercritical fluid. So, a fluid is called supercritical if both temperature and pressure are above this critical value. Say if we take the example of say carbon dioxide, then if we say this phase diagram of this carbon dioxide with temperature and pressure. So, we will have this, suppose this is line, says line, this is sublimation, then we can say this one, say this side it is liquid and this solid here, and here we can say this one gas, and say then we have this liquid line. So, we can say this one from liquid to gas, we can say this one evaporation line or boiling line, and then say if we are increasing the pressure and we can say and increasing the temperature. So, one point will reach where we can say this one the behavior of this carbon dioxide will be different from that of this, we can say carbon dioxide as gas or liquid. So, this carbon dioxide is useful solvent for supercritical fluid extraction, especially in food processing industries. The state and density of carbon dioxide is shown in this pressure temperature plane. So, whenever we can say this one pressure and temperature becomes more than this temperature and pressure, suppose above this 31 degree Celsius and 73.8 bar, then say in this zone we can say this one the shaded zone. So, we can say this one carbon dioxide behaves differently. So, in that case we can say this one above this critical point, say we can say this one this is we can say this one supercritical fluid. So, in this zone the entire fluid is called supercritical carbon dioxide, suppose for this case. So, supercritical fluids are known to provide good reaction media due to their, so we can say capacity to homogenize a reaction mixture, high diffusivity and controlled phase separation and distribution of the products. Okay. So, we can say this one physical and thermal properties of the supercritical fluids are in between pure liquid and gas. So, that is why we can say this one it behaves like, we can say this one liquid like density, then a reduction in the surface tension, then gas like viscosity and gas like compressibility properties, and diffusivities are higher than the liquids. So, we can say this one whenever we will be using a supercritical fluid for the extraction of particular target component, then we will be getting the help of this all the properties like this, say like this densities like liquid like density is not so high, but surface tension is decreased, then viscosity is like gas, and then we can say this one diffusivity values are higher than this, we can say this one liquid. So, that is one important point, and for that reason actually supercritical fluid can extract efficiently we can say the target component from the solid. Okay, so, if we talk about this carbon dioxide, its normal boiling point is minus 78.5 degree Celsius, but its critical pressure is 73.8 bar and critical temperature is 31.1 degree Celsius, and density is 0.468, that is not so high also we can say. Okay. Now, say whenever we will be talking about the supercritical fluid extraction, so we can say this one extraction of certain solutes from solids or liquids using supercritical fluid is a recent addition to separation technology. Solubility and selectivity of any solute in supercritical fluid extraction are functions of temperature and pressure. So, if we talk about any separation of a target component from the solid, say we can start with this, suppose carbon dioxide cylinder, then this is gone through this condenser, and say using this we can say this one brine chiller MEG and water, then this is actually passed through this CO2 pump to increase the pressure above this critical point, and then it is preheated, so that we can this temperature also remains above this critical point. Then whatever the product actually is coming out, that is we can say this one supercritical carbon dioxide. It will be now added to this extraction unit, or we can say this one where this supercritical fluid extraction will take place. After that, using the supercritical fluid, this extraction is over, then it is gone through this pressure control valve, and then we can say this one separator will be there. From there we can say the product will be separated here, and the whatever the carbon dioxide will be coming out, that can be to vent, or we can say this one sometimes it is recycled. Like the here actually you see this one, whenever we have this carbon dioxide, it is obtained from any source like this. Here in this case it is used from the carbon dioxide cylinder, but in some cases carbon dioxide will be available from the extraction vessel. So, it is compressed first, and then say we can say this one it is heated, then whenever it comes here, it will be like above this critical points. Okay. So, then in extraction vessel, so feed will be added here, and then the extraction, or we can say this leaching actually will take place here efficiently, and then it will go through this cooler and then depressurizing system, or we can say this one where pressure reduction will take place, then precipitation of the solute will take place, because whenever the pressure will be released, that time also temperature will be released. So, decreased, and then due to this decrease in the temperature, we can say this one, and due to this decrease in the pressure, the solubility of the solute in the we can say the solvent like carbon dioxide here will be decreasing. That is why the excess amount will be separated as the precipitate. Okay. And then whatever the carbon dioxide will be obtained from there, that will be again recycled to the system. Okay. Then it will be again converting into supercritical fluid. Okay. So, advantages of the use of this carbon dioxide as the solvent. So, there are so many advantages of the use of the carbon dioxide as the solvent in case of the supercritical fluid extraction over the other we can say solvents. Like carbon dioxide is inexpensive, it is non-toxic and generally recognized as safe gas, then non-flammable, we can say the available in high purity, easily removable from the extract, because whenever it will be going to this say knockout drum like this, where the pressure will be released, from there it can be separated very easily. Okay. And this one low critical pressure like only 73.8 bar, and we can say this one normal boiling point is minus 78.5 degree Celsius, and critical pressure is 73.8 and critical temperature 31.1 degree Celsius, and density is 468 kg per meter cube. It is also called as the cleanest solvent, because carbon dioxide does not react with this target solute, and that is why it extracts only, it dissolves only in carbon dioxide. After that it is separated very easily, then it is recycled. So, that is why we can say it is the cleanest solvent, and it does not contaminate the solute. Now, we will be giving some examples of we can say this one supercritical fluid extraction or applications, like the mostly these are used for the we can say this one food industries, like decaffeination of the coffee. Suppose coffee beans are soaked in water, then this is loaded in a we can supercritical fluid extraction vessel at 300 atmosphere pressure and 150 degree Fahrenheit temperature. There actually supercritical carbon dioxide solubilizes the caffeine, and the inert material will be separated from this caffeine in this we can see this one in water scrubbing vessel, where we can see this caffeine is transferred from carbon dioxide to water, then water is depressurized and this distilled away. So, this is one example. So, we can see this one we can separate this coffee from this coffee beans. Then extraction and recovery of active ingredients in natural products and in the food industries, then extraction of flavors, then fragrance and aroma from flowers like jasmine and rose or so many. Then extraction of the natural food colors, like this we can see the curcumin, vixen, this one from plants and fruits. then extraction of the vitamins, then antioxidants, then like beta carotene, then essential fatty acids, etc. Then extractions of oil from the flax seed and grains, then flavor and essence extraction from the spices also, then removal of pesticides and removal of the alcohol from wine and beer. So, there are so many examples of the supercritical fluid extraction, this one from the solid material, and like this almost 100% palm oil can be extracted and it is regarded as safe with organic solvent free extracts having superior organoleptic profiles in palm oil industry. Then cholesterol is shown to be soluble in supercritical carbon dioxide and even more soluble in supercritical ethane also. Its removal can also be improved through the coupling of carbon dioxide extraction with an adsorption process operating at the same extraction condition. Then carbon dioxide extraction in the supercritical mode has also proved efficiency for the production of the high quality cocoa butter from the cocoa beans. Okay. Now, we will be solving one problem on the supercritical fluid extraction. This is very simple problem, and say in a supercritical fluid extraction vessel, a naphthalene and chalk dust mixture is fed at 300 bar and 55 degree Celsius. So, 15% naphthalene is dissolved at this condition. Okay. So, and the pressure is now decreased to 90 bar through pressure reduction valve by isenthalpic expansion. Okay. Suppose in this extraction, suppose this is the supercritical fluid extraction unit. So, it is at we can say this one 300 bar and 55 degree Celsius temperature. Then suppose here carbon dioxide is added. Suppose this naphthalene plus chalk, these are there, and say we can say this one once this extraction process is over, then pressure, suppose this is say 300 bar pressure, then pressure is released actually with this, with the help of this, so we can say this one pressure releasing valve. Then so suppose it is going to this, we can say separator, there the pressure is 90 bar and temperature is decreased to 36, 90 bar then 36 degree Celsius. You see, whenever it is at high temperature and pressure, suppose this 15% solubility was here, but here it is only 2.5% solubility, like this 2.5% solubility of naphthalene is there. So, that is why this one at this temperature and pressure, suppose at this 90 bar and 36 degree Celsius, the solubility is 2.58%. So, it will be separated from the solution and will be collected like the precipitate. Then this carbon dioxide is again compressed to 300 bar and it is again fed in the supercritical fluid extraction unit. So, at say we can say 36 degree Celsius and 90 bar to 300 bar and 55 degree Celsius. Now, we need to calculate the amount of carbon dioxide required to extract 1 kg naphthalene and energy required for the extraction of 1 kg naphthalene. Okay. So, this is we can say very simple problem, and for that case actually say molar diagram is applied for this system, means say this naphthalene and say carbon dioxide, this one is supplied like this. Say entropy versus temperature is plotted here, and you see this one enthalpy lines are like 155 kilocalorie per Kelvin, this one, then say 145 kilocalorie per kg enthalpy line is this, then 135 kilocalorie per kg enthalpy line is this, and these are all we can see this pressure line. Suppose this is 90 bar pressure line and this is a 200 bar pressure line. So, this is 300 bar pressure line this way. So, this is 600 bar pressure line with different temperature, how it is varying actually it is there. So, from this problem whatever is given now we need to this one get. Suppose the initial condition is 30 bar and 55 degree Celsius. So, we can say 300 bar and 55 degree Celsius. So, we can say this 300 bar and 55 degree Celsius. So, we can say from this 55 degree Celsius and say 3 bar. So, we have this condition. So, we can say this one, we can write the initial condition or supercritical condition, that is we can say 300 bar and say 55 degree Celsius. So, it is supercritical fluid extraction system. Okay. So, that point 2. Then the problem is given like this: the pressure is decreased to 90 bar through pressure reduction valve by isenthalpic expansion, and then temperature becomes 36 degree Celsius. So, from point 2 actually this using this isenthalpic, this enthalpy line. So, it is coming down like this one and it is reaching to 90 bar, and that time temperature becomes 36 degree Celsius. So, then point 1 is we can say this one, whatever is there in the this one graph, like this, say 90 bar and 36 degree Celsius. So, we can say this is actually after expansion. After expansion, the pressure is released as well as this temperature is decreased. Okay. Then what is done? So, after hence it is separated from the solid, we will be discussing this one, and CO2 is compressed to 300 bar again at 55 degree Celsius. So, we can say this one. Now, from here say this one again it will be compressed to 300 bar. So, this point is we can say this one again it will come, then temperature will become 72 degree Celsius. So, we can say 300 bar and 72 degree Celsius. So, after compression, then fourth step is, so from 3 to again 2. So, we can say this one 300 bar and 55 degrees Celsius. That is we can say this one again it will be like this 300 bar in that will come to supercritical fluid extraction unit. So, this is we can say this is a total system. So, we will start at say 300 bar and 55 degrees Celsius, and isenthalpic we can say this one expansion will take place from point 2 to 1, means pressure will be released from 300 to 90 and temperature will be decreased from 55 to 36. Then in this condition, say suppose the solubility is 15% and in this condition solubility is only 2.5%. So, due to the solubility difference, the solutes actually will be separated as the precipitate. So, at point 1 we will be getting the product. Okay. So, we will be getting the product as the precipitate. Okay. And say from one point it is compressed, say 2.3. So, suppose from 1 to 3 actually it is compressed to 90 to 300 bar, and that time temperature will increase from 36 to 72 degrees Celsius, but the extraction takes place at 55 degrees Celsius. So, at that same pressure temperature is decreased. Okay. So, this is our say system, like this we can say. Then this energy requirement we can say this one for the compression from point 1 to 3. So, we can say this one energy requirement from 90 bar to 300 bar in the compressor is equal to. So, for this case it was 145 kilocalorie per kg to 155 kilocalorie per kg. So, it is 152 minus 145, that is kilocalorie per kg. So, that is coming out as 7 kilocalorie per kg. So, that is we can say this per kg carbon dioxide compression we need 7 kilocalorie this one energy. Okay. Now, we can say this one, we know the solubility of this naphthalene at, we can say this one at 55 degree Celsius and 300 bar, that is we can say 1.5. So, we can say this one decrease in solubility is 15% to 2.5%. Okay. So, we can say this one 1 kg carbon dioxide, so contains 0.15 kg naphthalene. Okay. And so, that is we can say this one at say 55 degree Celsius and this one initially, and 1 kg CO2 contains 0.025 kg naphthalene after expansion. Okay. So, whenever this pressure is released from 300 bar to 90 bar, then we can say this one for 1 kg carbon dioxide, the amount of, we can say this one naphthalene content will be decreasing from 0.15 kg to 0.025 kg. So, we can say this one the extracted naphthalene per kg carbon dioxide. So, we can say this one extracted naphthalene per kg carbon dioxide is equal to 0.15 minus 0.025 kg, that is 0.125 kg. Okay. Therefore, we can say this one 1 kg naphthalene is extracted by 1 by 0.125 kg CO2, that is coming out at 8 kg CO2. So, the first problem this one that is asked, that how much amount of this one carbon dioxide required to extract 1 kg naphthalene. So, we can say this answer is, so 8 kg CO2 is required to extract 1 kg naphthalene. Okay. So, that is the first this one question, and the second question is that the energy required for extraction of 1 kg naphthalene. Okay. We can say this one we have this one energy required. So, En energy required to compress CO2 from 90 bar to 300 bar is equal to, we can say 8 into 7 kilocalorie, that is we can say 56 kilocalorie. So, we can say this one for we can say this for 1 kg. naphthalene extraction. So, that is per 1 kg naphthalene extraction. Okay. So, we can say this one that way we can say this one use the supercritical fluid extraction system for the we can say the extraction of solutes from the we can say the solids. Okay. Now, we will be discussing about the equipment for leaching. So, so there are two different types of leaching equipments like we can say extraction units also like batch equipment and we can say this continuous contacting equipments. In batch equipment say we can say percolation tank is there, that is fixed bed one, then Pachuca extractor unit, that is air agitated one, then multi batch system also is there. In case of the continuous contacting equipment say vertical basket or Ballman extraction unit is there, then Hildebrand extractor is there, then Bonotto extractors also are there, and some horizontal basket extractors are there, some continuous belt extraction units also are there, and then rotocell extractors also are there. So, these are we can see these continuous contacting equipments. Few this one's pictorial views of the equipments are as follows. Like for percolation tank, suppose the solvent will be in from here and then say packed bed is here, packing material is filled here, and then we can say the solution will be out with we can say the solute, like this is a spray percolation system. Then full immersion system is like this where we can say this on a hold down plate is there and then packing material is here, but solvent will be in from the bottom and then we can solvent will be out from the top like this. And then Pachuca extractor is there, that type of thing using this air lifting. Okay. Then we have this Ballman extractor like this, it is also we can say one type of extraction unit, that is leaching unit. Then Hildebrand extractor also is like this, and then we have this Bonotto type extractor where we can say this one solids will be entering from here and then we can say this one extracted solid will be separated from this one bottom of this one through this conveyor belt. Like horizontal basket extractor also say suppose seeds will be, or we can say this one feed will be entering from here and then we can say this one, and or inert material will be discharged from the bottom of this we can say basket extractor. Okay. And like continuous extractor we can say this one belt type extractor, suppose this using this belt actually suppose solid feeds will be entering from here and then we can say this solvent will be supplied from this bottom of this we can say this one belt extractor, and then extracted solid or we can say inert material will be separated from here and we can say this micella also will be coming out from the other side of this we can say the extractor. Like rotocell extractor also, like here also so many we can say these rotating cells are available here and solid will be supplied from this top and we can say this one this what is called inert solid or leached solid, or we can say this one extracted solids will be coming out from here and this we can say this one extracting solvent is supplied from the top of this extraction unit. Okay. So, we can say this one thank you. In next class we will be discussing about the membrane separation technology.